We are mostly familiar with mechanical switches and how they are used to make or break an electrical connection or circuit, and also how we can speak into a microphone and have a louder version of our voice out of a speaker. Transistors basically do the same things to an electronic signal. In fact, the microphone and speaker relationship depends a lot on transistors. Simply put, a transistor is a semiconductor device which acts as a switch or an amplifier. In electronic circuits, transistors can be classified as BJTs, the bipolar junction transistor, and FET, the field effect transistor, which is further classified into NPN and PNP for the BJTs, then JFETs and MOSFETs for the FET. The most significant difference between the BJTs and the FETs to be the fact that the BJTs are current controlled, while the FETs are voltage controlled. The BJT transistor is usually a 3-terminal device with pins called base, collector, and emitter. The base is the control pin of the transistor and regulates the flow of current between the collector and the emitter, depending on the transistor. These pins are located differently. These are their symbols, the difference being in the direction of their arrows. The NPN requires a small positive voltage with respect to the emitter and current flowing through its base to turn on. That is, for current to begin to flow from collector to emitter. So the voltage at the collector should be greater than the voltage at the emitter if the current has to flow in that direction, while the PNP requires a small negative voltage at its base relative to the emitter and current leaving its base to turn on. That is, for current to begin to flow from the emitter to collector. So the voltage at the emitter should be greater than the voltage at the collector if current should flow in that direction. The BJT operates within 3 regions. The first is the saturation region. The cutoff region is next, and the active region, considering the transistor as a switch. We will look at the saturation and cutoff regions, and we will talk about the active region when we consider transistors as amplifiers. The saturation region is a region where the base triggers maximum flow of current between the collector and emitter. It's more like turning the knob of a tap, which in our case is our base. Turn it to the angle where maximum flow occurs in the pipe, and any further turning doesn't increase flow. If we have 12 volts on the collector of our NPN and emitter of our PNP and a small voltage is placed, and currents pass through the base to put it in saturation, we will notice for both NPN and PNP, the collector and emitter become equal in potential. For the NPN, our collector voltage disappears, taking up the voltage of the emitter with current flowing from collector to emitter, while for the PNP, the collector takes up the voltage of the emitter with current flowing from emitter to collector. Notice we have positive VBE for NPN and negative VBE for PNP, and we mean the base emitter voltage. For NPN, the base is more positive in voltage than both the emitter and collector. So we have VB greater than VE and VB greater than VC, while for the PNP at saturation, the base is the lowest in potential amongst all 3 pins. The cutoff region is the region where the flow of current through the base is reduced to a point where there is no flow of current between the collector and the emitter. So our transistor has to operate in these 2 regions: the fully on region, which is the saturation region, and the fully off region, which is the cutoff region, for it to operate as a switch. This brings us to an important property of transistors, called the DC gain, usually represented as HFE or beta. The DC gain is the ratio of the collector current to the base current. In other words, if you send 1 unit of current into the base, and because of that the transistor sends 50 units through the collector and emitter, So the DC gain is 50. It's more like the multiplication factor of your input that determines output. Let's make this practical. We have a 3-volt LED, and we decide to switch it on and off with the help of the very famous 2222 NPN transistor. So we connect our transistor to our LED as shown. We can see we do not know the value of our resistors. So to find them, we have to first find the voltage across the resistor, and then, with the current we will allow go through them, we will find their resistance. Since we are operating transistor as a switch, we'll have no voltage drop across those terminals when they are on. So, if you look at the circuit path and some voltages, we can see we have 12 volts for our power source, minus VR1, which is the voltage across R1, minus VLED, which is the voltage across the LED. And these voltages will sum up to 0. So, since we're using a 3-volt LED, we can bring that value into the equation as VLED. Then we find VR1. So, if we make VR1 the subject of formula, we're going to be having VR1 to be 9 volts. Now if you look through the datasheet for this transistor, we can see the arrangement of the pins. If you scroll to the table labeled on characteristics, we can easily see a role for DC current gain. We can see it has different minimum values, which is dependent on the collector current, IC, and the collector emitter voltage, VC. But since we're looking to power on an LED, we will need a collector current of 20 milliamps, which falls within the range of 10 to 15 milliamps, which has minimum better to be between 35 to 100. To design this, we have to take the lowest option, or even lower for our beta, just so we are sure our transistor is saturated, no matter the operating conditions. So for this design, we will assume a beta of 20 units while IC, which is the current through the LED, would limit it to 20 milliamps. So we use the formula V equals IR to find the value of the R1 resistor. And if you do that, we'll have R1 as the subject of formula, which becomes VR1 over IC, and then bringing in the values, 9 volts and 20 milliamps. When we divide them, we have 450 ohms. But since we don't have 450 ohms, we take the next available value but higher than 450 because we really do not need more than 20 milliamps going through the LED. So if we let more pass, we shorten the LED's lifespan. The more current, the shorter the life of the LED. So we picked 470 ohms, and if we calculate backwards, we'll find out that 470 ohms will allow 19 milliamps go through the LED. So we are fine with that. Power rating of resistor will be 171 milliwatts. Okay, if we multiply our current, which is 19 milliamps, by the voltage across the resistor, which is 9 volts, we'd have 171 milliwatts. And if we double this 171 milliwatts value, we would be having 342 milliwatts. So we can then push it up a little to the 500 milliwatts resistor, since that's what is next available in value. So our own resistor is going to be 470 ohms and 500 milliwatts. So how much current do we need to pass through our base to have the collector allow a current of 19 milliamps through it? We use collector current divided by HFE, which is 19 milliamps divided by 20. And this gives us 0.95 milliamps. Next is, what resistor value do we have to put on our base to achieve a flow of 0.95 milliamps through the base? So, if we consider the circuit path from the base to the emitter, we have to acknowledge the voltage drop experience between the base and emitter. We will call it the base emitter voltage. So the question is, for us to have 0.95 milliamps flowing through the base resistor, what voltage should we have across it? If we go back to our datasheet, Same table as before. On the last row, we see base emitter saturation voltage at 0.6 volts, which means if saturation is to happen, the VBE should at least be up to 0.6 volts. So we take a higher voltage to create a cushion, just in case of unforeseen negative operational conditions. So we take 0.8 as our value for VBE, recalling that voltage divides across resistance. In series, we can easily know we will have 11.2 volts across the base resistor, which we got by equaling the voltage across the voltage source to the voltage across the resistor, and the voltage across the base and emitter pin. Because this path is the path of a complete circuit, so we have this voltage splits across this resistor and across VBE. So if we solve for that, we're going to have our VR2. That's the voltage across R2 to be 11.2 volts. With this, we can now find the value of the base resistor to be 11.2 divided by 0.95 millions, which gives us 11.8 K. Since we can't get 11.8 K ohms resistor, we would use 10 kilo ohms. We're using a lesser resistor because we want to ensure enough current flows in to get us at saturation. If you calculate backwards, we'll see 10 kilo ohms will allow a current of 1.1 milliamp. The power rating of the resistor we will need should be at least 11.2 times 1.1 milliamp, which will give us 12.3 milliwatts. Doubling that value would give us 25 milliwatts, approximately. So we can use the 250 milliwatts type resistor, and we will be fine. So let's see what happens when we turn on our power supply, and let's see if we can actually confirm if this current flowing through the base and flowing through the collector would be accurate. So we turn on our power supply. We have this meter to show the current going through our base. We ought to have 1.1 milliamps going through the base from our calculations. You can see this meter shows 1 milliamp and back to zeros. That's because the meter can display currents below 1 milliampere. So once the current drops below the threshold, it shows zeros. While here, we have 18.7 milliamps going through the resistor. So let's check the collector emitter voltage and the voltage at the base with respect to the emitter, VB. Okay, so for our collector and emitter, we can see we have approximately no voltage between them. Okay, so we are actually in saturation. Let's get the base emitter voltage. For the base emitter voltage, we have 0.72 volts. So let's try the same with a PNP powering a DC fan. We'll be using the S8550 transistor, and we would connect as shown. You can pause the video here, download the data sheet for the transistor, and try out the calculations to get R1 and R2 yourself. Then come back. It's also a good place to click the like button, subscribe, and also leave a comment about your experience finding these values. So we have a DC fan whose rating is 12 volts and 0.18 amps. So we'll increase our voltage across the source to be 15 volts because we want 12 volts across the fan. So let's find what resistor we'll place after our collector to make this possible. Since our transistor operates as a switch and the fan will have 12 volts across it, our resistor should have 15 volts minus 12 volts across it, which would be 3 volts. So, of course, we have 15 volts here. And if you notice, this is positive and this is negative. So we have 15 volts there. Then we would have this is our collector. This is our emitter. So, if you have this operating as a switch, would have this place. and this place to have same voltage level. So it means that we can ignore the voltage drop across this place, because if it's a switch, then it's going to just be operating as a wire, and third be no voltage drop across it. So next we have the voltage drop across our fan, which we intentionally want to be 12 volts. So we put in our 12 volts there. Then we have the voltage across our 1, which is what we're trying to find. So we have 15 volts minus 12 volts, which is equal to the VR1. And then if we simplify that, we get our VR1 as 3 volts. If the resistor is to pass 0.18 amps, when it has 3 volts across its ends, the resistance automatically then becomes 3 volts, divided by 0.18 ohms, and we have 16.7 ohms. So because we don't have 16.7 ohms resistors, we can use 18 ohms. We use a higher resistance to ensure we don't exceed the maximum safe operating current of the fan, which happens to be 0.18 amps. So an 18 ohms resistor will give us 3 volts, divided by 18 ohms, which would give us 167 milliamps of current. Next we find the power rating of the resistor, which would then be P equal to IV, which is 3 volts times 167 milliamps, and would give us 501 milliwatts. If we double that, then we'll see we can safely operate the 1 watt resistor in this case. So that's what we're going to be using. We're going to be using an 18 ohm 1 watt resistor. Next, let's try to find how much current we have to pass through our base to make our transistor saturate at 167 milliamps current. So let's go to our data sheet. Here we see minimum HSF is about 40. So to ensure saturation we go lower. We will take the HSF to be 20. Using the formula IB equal to IC, all over HFE would have 167 milliamps divided by 20, which would give us 8.35 milliamps. We go back to our datasheet to check what base emitter voltage we need to get saturation. So we find VBE set, and it's typically about 0.98 volts. So we can go up to 1 volt for VBE. From the equation V equal to VR2 plus VBE, we can equate that to 15 volts. So we have to use this equation to find our VR2. And if we do so, we would have our VR2 to be 14 volts, which means we have 14 volts on our base resistor. And the current through the resistor, we already have that to be 8 milliamps. Therefore, resistance value for our resistor is VBR divided by IB, which is 14 volts divided by 8.35 milliamps. And that will give us 1.7 kilo ohms. Now, since 1.7 kilo ohms isn't available, we use the closest value, but lesser. Rather than have lesser currents go through the base, we actually need more currents to ensure saturation. So we would use the 1 kilo ohm resistor. So for 1 kilo ohm our IB would be 14 milliamps. So what power rating should the resistor we would use have? So we find that by P equals to IV, which is 14 milliamps times 14 volts, and we have 196 milliwatts. Okay, so we double that, and we get 392 milliwatts. So we can use the 1 of a 4 watt resistor here. So if we then turn on our power supply, we'll see we have our fan turned on. So let's do that briefly. Okay, we have our DC fan here. And we have this meter connected to the base as an ammeter. So we read the current through the base, the current for the collector, and the fan also, we'll see from here. So I turn on my power supply and the fan starts to turn. You can see it. $160 milliamps going through the fan. And we have 13 milliamps. 13.5 milliamps going through the base. Okay, so from our calculations we had We're supposed to have 14 milliamps going through the base and approximately 160 milliamps going through the fan. So, another thing I want us to do is to check the voltage across the collector and the emitter to confirm that we are actually at saturation. So, we take the collector emitter reading and we are actually having 177 millivolts there. Like the voltage difference between both of them is very little, so we see we are at saturation. Okay, so let's check the BER base and emitter voltage. We'll be having minus 0.8 volts.